All right. I hope you all had a good weekend. So no special announcements today other than we have our usual homework due on Friday, and you're doing lab 2 this week, and there is no pre-lab for lab number 2. Okay, so what we did last time is we kind of did a bit of a big summary of how we could apply Gauss's law in situations where it's going to be useful. And we thought of 3 different situations. Those included charge distributions that are spherical, charge distributions that are planar, and those that are cylindrical. And what we focused on was how we could evaluate the integral in Gauss's law, the integral of the E dot dA around our closed surface. And so for spherical symmetry, what we found is that if we use a spherical surface, it makes evaluating that integral easy because the electric field is going to be radial. The normal vectors on our spherical surface will also be radial. That means the dot product in E dot dA will vanish. Furthermore, if we have a spherical surface centered, sharing the same center as a spherical charge distribution, then the electric field will be the constant at every point on the surface, and it factors out. And we end up getting, for that integral, E times the surface area of the sphere, which is 4 pi r squared. When we thought about the planar geometry, what we decided is that a surface with flat tops and bottoms would be useful. In that case, what we ended up getting was flux from only the top and bottom surfaces. And when we evaluated the integral, we got 2 times E times A, where A is either the area of the top or bottom surfaces, which would be the same. And the factor of 2 is from the fact that you get flux through the top and the bottom. And then finally, for the cylindrical symmetry, we chose a cylindrical Gaussian surface, and we got E times the area of the curved surface, because the ends of the Gaussian surface, the cylindrical Gaussian surface, don't contribute to the flux. Okay, we did an example where we thought we did an example where we used the cylindrical geometry. We imagined a uniformly charged sphere of radius capital R, and we tried to calculate the electric field both at points outside the sphere and at points inside the sphere. Sorry, not the sphere. Points inside the charged cylinder and points outside the charged cylinder. And we got the following results. For a point inside the cylinder, E was equal to the charge density rho times the position R divided by 2 epsilon naught. And then when we were outside, we got this other result, which involved the radius capital R of our charged cylinder. So what I want to do is I just want to finish off this example by plotting what this electric field looks like. So we're going to say that for points inside our charged cylinder, the electric field was proportional to R. So it increases linearly as we move away from the cylindrical axis. And for points outside, E is proportional to 1 over R. So it drops off as we move further and further away. And so let's make a plot of that. We're going to make a plot that has the electric field magnitude on the vertical axis and the distance away from the cylindrical axis on the horizontal axis of our plot. So if we draw our charged cylinder, this is what it looked like. This is just a section of that cylinder. So we imagine like it was very long. So it continues in both the positive and negative directions. This is the radius of our charged cylinder, capital R. And then if this is our cylindrical axis, we're thinking about points. So here would be a point outside of our cylinder. Let's call that P outside. And so in this case, R would be this distance. If we were looking at a point inside, you know, maybe here, so we'd call P inside, then R would be this distance, the distance from the axis of the cylinder to our point. Okay, so when we're inside, what we saw was the electric field would increase linearly. And so that would be true up until we get to a point where little r, the distance from our cylindrical axis, equals the radius of our charged cylinder. Okay, and so here is proportional to r. And then we could go back to our vertical axis and say, okay, when we're inside the cylinder, the electric field has a strength of rho times little r divided by 2 epsilon naught. So when we get right to the edge where little r is equal to capital R, the electric field strength would be rho times capital R divided by 2 epsilon naught. If we think about a point outside, the closest we could be is right at the surface. So again, little r is equal to capital R, and we would get the exact same expression for the magnitude. So they're consistent. The two expressions agree at that one point where little r is equal to capital R, right at the surface of our charged cylinder. And then outside, we have a 1 over r dependence, and so this electric field drops off something like this. So this is proportional to 1 over r. And so that's how the electric field varies. You can kind of build a bit of intuition by thinking about, like, why does the electric field increase when we're inside the cylinder but move away from the axis? Well, the idea is, from Gauss's law, we know that it's only the charge inside of our Gaussian surface that contributes to the electric field. So as we move further and further away from the axis, and we choose a bigger and bigger Gaussian surface, it encloses more and more charge, and so the electric field gets stronger. Once we get to the outside, as we move further away, our surface gets bigger, but the Q enclosed doesn't increase, and so for that reason, the electric field strength decreases as we move further and further away. Okay, I want to do one other thing with this example, and let's focus now. Focus on the electric field outside the charged cylinder. So this is the case for little r is bigger than the radius, and we know that in this case, the electric field is equal to rho r squared divided by 2 epsilon naught times r. Okay, so what I'm going to try to show, and it will be fairly easy, I think, is that when we have this cylinder of radius capital R, and we're looking at a point outside, for all we can tell, that looks exactly like a 2D line of charge. It's as if all of the charge is concentrated right on the axis of that cylinder. And so that's what I want to try to show. Okay, so the charge density of our cylinder is rho is whatever its charge is divided by some volume. And so let's just take a section of this cylinder. And so I'll take this section here, and maybe we'll shade it blue, something like this. So what I'm going to do is I'm going to say that blue shaded cylinder has a cross-sectional area A. And so we'll call this the cross-sectional area. And we'll give it a length L. Okay. So if I knew all the total charge of that blue shaded section of our cylinder, and then I divided by the volume, that would tell me the charge density. Okay, and so if we tried that, we would say, okay, rho is equal to Q divided by the volume. But the volume of that blue cylinder is just the cross-sectional area times the length. And so what I'm going to do is I'm going to multiply by that cross-sectional area. And so that means that, let's see, rho times the area is the charge per unit length. And what symbol have we been using for charge per unit length when we talked about, say, a charged wire or something like that? Lambda, that's exactly right. So this combination of rho times the cross-sectional area is one way to define the charge per unit length of our cylinder. So this is rho is the charge per unit volume, and lambda is the charge per unit length. So what I want to notice is that we have this expression here, rho times r squared. So what we're going to do is we're going to say, all right, let's take this electric field expression. E is equal to rho r squared over 2 epsilon naught r. So I just wrote it down exactly what we had. Haven't made any changes. Here's what I'm going to do. I'm going to multiply the top by pi, and I'm going to multiply the bottom by pi. Right, so I'm just multiplying by 1 in a funny way. If I do that, what I could do is I say, okay, here's rho, and then I have this pi r squared, and then in the denominator, I'm going to write this as 2 pi epsilon naught times r. So this pi r squared in brackets, what is that? It's the area of a circle, and our cylinder has a cross-section of a circle, and so that's exactly the cross-sectional area of our cylinder. So this is A, and so what we have then is the electric field is rho times A divided by 2 pi epsilon naught times r. But rho times A is exactly the charge per unit length that we just worked out. And so that means for our charged cylinder, so at a point outside our charged cylinder, E is equal to lambda over 2 pi epsilon naught r. And if you look back in our notes, that's exactly the result that we got for a simple line of charge. So this is the same result obtained for a two-dimensional line of charge. Sorry, I shouldn't call it two-dimensional. I should call it a one-dimensional line of charge, right? We're thinking of a line of charge that has no radius. It's just an infinitesimally small line of charge that just continues in one direction. Okay, so let's just draw that then. If I have a charged cylinder of some radius r, and so let's just imagine this keeps going. Here's our radius, capital R, and here's our cylinder axis. And I'm at some point P that's outside, and this is a distance r away. Then the electric field at P is equal to lambda over 2 pi r epsilon naught. And if I compare that to just a line of charge that just continues on and on and on, right? So this is all plus, let's say all charge positive. As long as I'm the same distance away, and so let's see, that's about something like this. So if this is the same distance r, E is equal to lambda over 2 pi epsilon naught times r. So these look the same. So that's kind of a nice little bit of insight that, you know, is not obvious before you solve the problem. We could have also done a uniformly charged sphere. And if we look at a point outside of that sphere for the electric field, it would look exactly like a point charge, as long as our point charge with charge Q has the same total charge as our sphere. Okay, so that's kind of this insight, is that all that matters is the enclosed charge, whether it's kind of distributed uniformly through a volume or concentrated at a point or on a line. None of that matters as long as the Q enclosed is the same. All right, good. Any questions? Okay, so what we're going to do now is we're going to switch gears and we're going to start chapter 7. So we're going to start chapter 7 in OpenStax University Physics Volume 2. And the topic is electric potential and potential energy. So in some ways, we're mirroring some of the progression that you probably followed in Physics 111, where you started by talking about, I don't know, forces and stuff like that, and then you move on probably to talking about energy and things like that. And so we've done the same thing. We developed this idea of electric fields exerting forces on charges. If the electric fields happen to be constant, then we could get a constant acceleration, use our kinematic equations. One of the challenges of always working with forces and fields is that these things are all vector quantities. And so it makes the math a little more challenging because we have to worry about the directions of things all the time. If we can develop a concept of like potential energy for the interaction between charges, then we can start working with quantities that are just scalars, they're just numbers, and some of the calculations become a little more simple. So let's see if we can do that. In order to get there, we're going to have to do a bit of vector analysis, but it's not that bad. So we're going to build on what you already know from Physics 111. So we're going to recall the work kinetic energy theorem. And so, you know, the common way to think of work is force times displacement. And that's sort of right. That's a simple definition. What it neglects is the fact that the only component of the force that contributes to work is the component that is parallel to the displacement. Okay. So the most general statement of the work kinetic energy theorem is that the change in kinetic energy is equal to the work, and the work can be expressed as the integral of f dot ds. Okay, and the integral is going to go from a point 1 to a point 2, and so we're going to follow a particle along some path, and we're going to, for every step along that path, we're going to evaluate f dot product with the displacement, and then we're going to add up all those little steps. That's what this expression means to get the total work, and that has to be equal to the change in kinetic energy. So as a picture, what this would look like is maybe we're going to have some complicated path, and we're going to start at some position 1, and we're going to end up at some position 2. So this will be like our initial position, and this will be our final position. And what we're going to imagine is that we have some particle, and that particle is moving along the path from 1 to 2. And so at every point along this path, it has some displacement, and that displacement is going to be parallel to the path. So at the position I happen to choose between points 1 and 2, that red displacement ds is tangent to the path at that point. And then there's going to be some force maybe acting on this particle. So maybe this is one of several forces that are acting on this particle, and we might ask the question, what is the work done by this particular force? Well, it's going to depend on the magnitude of that force and also on its direction relative to the displacement. Okay, so that's fine. This means that the dot product that we have to evaluate, this F dot ds, is just the magnitude of the force times the size of the step, the magnitude of the ds vector, times the cosine of the angle between them. And so this, it's kind of nice. We just did Gauss's law, which involved dot products. And so here's another case of a dot product. But we know a lot about dot products already. What we can say is, what I could do is I could break my force up into components. I could break my force into a component that, let me move my label here. So here's my force F. And so I could have a component that is perpendicular to the displacement, and I could have a component that is going to be parallel to my displacement. And it's only the part F times cosine of theta, which is equal to F parallel, that is going to contribute. So what we could do is we could say this is the same thing as F cos theta times ds. I just changed the order of the factors in this expression, but this F cos theta is just F parallel. And so this is F parallel, the component parallel to the displacement that contributes to the work. So only the component of F that is parallel to the displacement at ds contributes to the work. Let's call this work W. And so this integral is equal to the work, and it's also equal to the change in kinetic energy by the work kinetic energy theorem. All right, so what I want to do is I want to do this calculation. Let's actually evaluate the work for a problem involving charges in an electric field. So let's see how we can do this. So we're going to apply the work kinetic energy theorem to a point charge, let's say little q, moving in the electric field due to another point charge. We'll call it capital Q. All right, so we'll start just by drawing a picture. I'm gonna leave myself some room to make a decent picture here. So let's say this is the point charge capital Q. This is the one that is creating the electric field. And so we know that for a point charge, the electric field is radial. And so it's looking something like this. Okay. And what we're going to imagine is that we're going to take a second point charge, little q, and we're gonna move it from position 1 to position 2. And in order to calculate the work, it only depends on the starting point and the ending point. We could choose for our calculation, let me rephrase that. Our work, it requires us to pick a path from our initial point to our final point. And we can choose whatever path we want. I'm going to choose, in this case, to pick the simplest possible path, a straight line from 1 to 2. And so we're going to have point charge Q here, and it's going to move along a straight line from point 1 to point 2, and we're going to see how much work was done. So we're going to calculate the work for Q to move along a straight line from, let's say, position 1 to position 2. Okay, so what we have to do is we have to draw our displacement vector. So I'll draw my displacement vector like so, and these red lines are the electric fields. So this is a nice, convenient choice for us to make because we have to evaluate a dot product, and we've selected a path where the displacement ds is always parallel to the electric field. So for our straight path, we have the electric field parallel to ds such that E dot ds is just equal to E times ds. Okay, we get the cosine of 0 degrees, which is a factor of 1. Our displacement is in the radial direction. So we can write ds is equal to dr, right? It's a change in the distance from capital Q, which is just the radial distance from capital Q. All right, yep, go ahead. Because I evaluated the dot product, right? So this, here, we could do it in 2 steps. We could say, this is equal, the definition of dot product is we take the magnitude of our 2 vectors and times the cosine of the angle between them. But for our current geometry, that angle is 0. And so this becomes, cosine of 0 becomes a 1. And the magnitude of the electric field and the ds, I could just draw those without vector signs. Yeah, good. Okay, so what we want to do is we want to calculate then the change in kinetic energy, which is equal to the work, is this integral of f dot ds. Now we've just shown that this dot product goes away. And so this is going to be the integral. Sorry, what have I done? I've kind of left out a bit of a step here. I've made an omission. Does anyone know what it is? When I calculate the work, I have to do the dot product of a force times the displacement. But I've just written the electric field. What's the force on charge Q in an electric field? Q times E, that's right. So here, the force on Q is Q times E. And so when we evaluate F dot here, let me not change my notation. We'll just use F for the force. So F dot ds is the same thing as Q times E dot with ds. Okay, so this is going to be 1 to 2 of Q times E dot ds, which is the same thing as from 1 to 2, because the dot product goes away, and ds is in the radial direction. I'll write it as a dr. And then finally, what we could do is we could put in the strength of the electric field. And so this is the integral from 1 to 2 of Q. Now the electric field due to capital Q is Coulomb's constant times capital Q divided by r squared dr. Okay, and so this problem is not so difficult to solve. We have a bunch of constants. Coulomb's constant, little q, and big Q are all not changing. And so we could take them outside the integral. So we'd have Ke Q times Q, integral from 1 to 2 of 1 over r squared dr. What's the integral of 1 over r squared with respect to r? What happens to the power? Do we increase it or decrease it? We increase it by 1. So our current power is -2. So after the integration, we'll have r to the -1. We raise the power by 1 and then divide by it. So we have to divide by -1, which introduces a negative sign. And then we have to evaluate between our limits. Our initial position is our starting point, and our 2 is our final position, our ending point. Okay, so the change in kinetic energy is going to be equal to Coulomb's constant times the product of the charges. And then we'll put the minus sign over here. And then I have 1 over r from position 1 to position 2, which is minus Ke Q times Q. And then it's 1 over r2 minus 1 over r1. All right. So remember, this is the final position, and this is our initial position. Okay, so let's just go back and let's look at our picture. And let's just imagine both point charges are positive. If that was the case, would we expect our charge, little q, to gain kinetic energy or lose kinetic energy when it moves from 1 to 2? Think about the force between these two charges. Is it attractive or repulsive? It's repulsive. So is little q speeding up or slowing down? Speeding up. So we expect that we've gained kinetic energy. And so let's check if this works. Okay, so if Q and little q are both, or let's say are positive, we expect little q to gain kinetic energy as it moves from 1 to 2 due to the Coulomb repulsion. Right? The electrostatic force between these two charges is repulsive, so the large charge is pushing the little one away, and so it should be speeding up. Okay, so we want then the change in kinetic energy, delta K, to be positive, because that would be 1/2 mv2 squared minus 1/2 mv1 squared. So if it gains speed, v2 would be greater than v1, and so that should result in a positive quantity. And let's compare that to minus ke q times q times 1 over r2 minus 1 over r1. So R2 is further away from capital Q than R1. And so 1 over R2 is a smaller number than 1 over R1. And so 1 over R2 minus 1 over R1 is a negative quantity. So this is less than 0. But then we take that negative quantity that's in the brackets and we multiply it by minus KEQ times Q. Since both charges are positive, overall, our work is positive. And so therefore, V2 is greater than V1, and our charge has gained kinetic energy as expected. Therefore, V2 is greater than V1, and Q has increased its speed / kinetic energy. Okay, so that's expected. All right, fair enough. I won't write it down, but what would happen if, say, little q was a negative charge? Then everything we wrote down is the same, except for when we do the final product, we have minus times this R2 minus 1 over R2 minus 1 over R1. That negative sign combined with the brackets would be positive still. But if Q was negative, then we would calculate a negative work and our little charge would slow down, okay? Because it would be attracted back to the large charge. Okay, good. I want to do one other thing with this example, and I want to show that what we could have done is we could have chose a different path between our 2 points, 1 and 2, and I want to see what happens when we do the calculation following this alternative path. All right, so let's repeat the work calculation using the same points 1 and 2, but a different path between them. I can tell you what's going to happen. We're going to find the exact same result for this work. And if you think back again to Physics 111, we probably encountered forces for which the work was independent of path. That could be, for example, the gravitational force. And forces that the work was dependent on the path. Friction is an example of that. We're going to find that for this electrostatic calculation, we're going to have a work that's independent of path. And what that allows us to do is define a potential energy associated with this electrostatic force, just like we have a gravitational potential energy. So if I have my pen here and I move it from position 1 to position 2 in a gravitational field, there's some change in potential energy associated with that. But if I move it from 1 to 2 along a different path, there's still the exact same change in gravitational potential energy. It's just mg times the change in height. And it doesn't matter how I go from 1 to 2, as long as I have the same starting and ending points, this change in potential energy is always the same. And we're going to want to do something similar for our electrostatic force. Okay, so I'll draw my positive charge here. We'll draw its electric field. Okay, so there it is. I'll draw my same 2 points. Here's point 1 and here's point 2. Okay, but this time, what I'm going to do is I'm going to follow a path that's a little bit different. I'm going to draw these kind of radial lines around here. Let's see how well I can do it. Okay, so there's 2 radial lines. And what I'm going to do is I'm going to follow this path. I'm going to follow a path from here and then go up here. So we'll first go along here, then we'll go along here, and then we'll come back to 2. Okay, so when we do this, our path has like these 3 little segments. We follow first a inner circular arc, then we follow electric field line along this radial path, and then we take the outer circular arc back down to point 2. And so for every one of these, what we'd have to do is we'd have to define these displacement vectors, like we'd have a ds1, something like this. And over here, we'd have a ds2. And then over here, we'd have a ds3, like so. But at ds3, the electric field is this direction, and at ds1, the electric field is in this direction. And in both cases, we have the displacement and the electric field being perpendicular. And we have to do this forced dot product, Q times the electric field. So essentially, we need to do the dot product with the electric field with these displacements. And for these 2 paths that are these circular arcs, that dot product will vanish because the angle between ds and E is equal to 0. So for paths, say 1 and 3, and so I guess I could label them, right? So we could say, here's path 1, here's path 3, and here's path 2. So for paths 1 and 3, E is perpendicular to ds. So therefore, F dot ds is equal to Q times E dot ds is equal to 0. So only path 2 contributes to the work. And in this case, along path 2, E is parallel to ds2. And if you do the calculation, what you'll find is it's exactly the same as the previous example. All we're going to do is the integral of Q times E times ds2, and that's going to go from distance R1 from the capital Q to a distance R2. We're going to get the exact same result as before. Okay, so the work due to path 2 is identical to the previous example. So therefore, the work is equal to this F dot ds along path 1 plus F dot ds along path 2 plus F dot ds along path 3. But we've already argued that the first one and the last one are going to contribute nothing. And then we already know the result from before is, what was it? It was minus KE times Q times 1 over R2 minus 1 over R1. And so therefore, the work, which is equal to the change in kinetic energy, is going to be minus KEQQ times 1 over R2 minus 1 over R1, which is exactly the same as before. Now, that's not really a rigorous proof. I've chosen 2 paths that made the calculation easy to do. But you could say, well, okay, maybe it's the same for those 2, but if I choose some third really complicated path, then maybe I'll get a different answer. Well, what you can always do is you can take any arbitrary path, make it as complicated as you want. Maybe it has little loops and things like that. You can always take an arbitrary path and you can break it into infinitesimal steps that are either radial, so that they're parallel to the electric field, or these circular arcs that are perpendicular to the electric field. All the little bits that are circular arcs aren't going to contribute any work. All the little bits that are radial will contribute work. And if you add up all the little radial bits, it'll do just the same as if you went directly from 1 to 2 along that straight radial path, and you'll get the same answer. Okay, the reason you can always break your arbitrary path into radial and like little sections of circular arcs is because you can make those sections infinitesimally small, and you make them as small as you need to in order to make the smooth path, whichever one you chose. Okay, so no matter which path you choose from 1 to 2, the work will always be the same. It depends only on the initial and final positions on the, let's say, starting and ending points. Okay, another way of saying the same thing is that the work done by the electric force is independent of path. The work done by the electrostatic force is path independent. Okay, when we have this case, when the work doesn't depend on path, then we can say, we call that force a conservative force. If you think of friction, right? Let's think of a force where clearly the work does depend on direction, right? Let's say I want to slide my phone along this desk from this edge to this edge. I could do it like this. In that case, the friction force, the kinetic friction force is always exactly opposite to the direction of the motion. And so when I do the dot product, I'm going to get a cosine 180 degrees. It's going to bring in a negative sign. I'll calculate negative work, which tends to take kinetic energy out of my system. That kinetic energy gets converted into heat in the table. Now, if I have the same starting and ending point, but I take my phone and I slide it like this, well, it's still always true that the static or kinetic friction force is always opposite of the displacement. And so I'm just going to have a longer path that always has a contribution to this negative work by the kinetic friction. And so if the path is longer, I have more heat generated, more kinetic energy taken out of my system. Okay, and so that's the difference between conservative and non-conservative forces. So forces for which The work is path independent are called conservative forces. And so the last thing I'll write down is that for these conservative forces, we can define potential energies, and that's what we're going to do next time. We'll define the electrostatic potential energy. So we can define potential energies for conservative forces. We will define the electrostatic potential energy next time. All right. Thank you very much. We'll see you on Wednesday.
Thank you.
All right. See you later.